Hi, my name is Ava Martino, and I'll be presenting on Lab 2 of Physics 2212, Magnetic Field of a Bar Magnet. In the introduction, I'll outline the purpose of the lab and introduce some key concepts used during the experiment. Next, I'll go over the details of the experiment and perform some calculations for the dipole moment. I will then create a computational model to see a visual representation of a magnetic field in GlowScript. And finally, I'll address the discussion questions. The purpose of this lab is to determine the relationship between the distance from the magnetic field and the magnitude. Then we will create a GlowScript code in order to visualize the magnetic field. In this experiment, the system is the magnetometer, while the surroundings consist of the bar magnet, Earth, and everything else. For a preview of the results, the magnetic dipole moment is 0.525 amphimeters times meters squared, and n is negative 3.62. Some key concepts used during this experiment are the Biot-Savart law, which is a principle in electromagnetism that describes how a steady electric current produces a magnetic field. Another concept is the distance dependence equation. Both equations can be seen at the bottom of the slide. So the procedure for this experiment starts by first finding a magnetometer app on your phone to collect the data, and then determining the location of the magnetometer sensor on your phone. Then you need to measure the on-axis magnetic field by measuring the distance between the magnet and the sensor. Finally, we had to measure the off-axis of the magnetic field. For the on-axis data, I used the app and a ruler to find the distance and the magnitude of the magnetic field. I put the data into the Excel sheet provided and graphed the natural log of the x component versus the natural log of r. We then did some calculations in order to determine the magnet's magnetic dipole moment by using the distance dependence equation. We solved for k, which we found to be 1.05 times 10 to the negative 7, and n was equal to the slope of the line from the graph in the previous slide, which was negative 3.6273. This gave us a result of the dipole moment mu to be 0.525 amphimeters times meters squared. For the off-axis results, I positioned my phone's magnetometer sensor a distance d from the magnet in both the x and y direction. Then, I put the data into the Excel sheet. I then collected the corrected y component by subtracting the magnitude of the Earth's magnetic field from the magnitude of the magnetic field measured. The average perpendicular distance was found to be 0.230988 meters, and the average B net magnitude was found to be 1.707 times 10 to the negative 4 Tesla. Now moving on to the GlowScript code part of the lab, I created the dipole definition equation by plugging in the Biot-Savart law. I then created 6 arrows. 2 arrows represent the magnetic field on axis, and 4 arrows to represent the magnetic field perpendicular to the axis, as well as another arrow to represent the magnetic field 45 degrees from the axis. I then plugged in the d-perp and magnitude of the dipole moment that I calculated from my observations. Here are my results. Some errors that may have occurred during the experiment were that there could have been some other magnetic field that affected the magnetometer sensor, causing the data to be slightly inaccurate. Another error that could have occurred is the magnetometer sensor's predicted location could not have been its exact location. And then there could also be some calculation errors that could have occurred when finding the dipole moment. Finally, to answer the what-if questions. What if you hadn't done that and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? The x and y component would be skewed in the direction of the magnetic north, so the values calculated would be different. However, the z component would stay the same. Now, imagine you had 2 identical magnets. What if you redid the experiment, but instead of using a single magnet, you used the 2 identical magnets stuck together end to end? How would you expect your measurements to differ? The combined magnetic fields of both magnets would increase the magnitude of the field, and because of this, the increased distance between the magnetometer and magnets will decrease because of the larger effect.